RCT, the reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node, and that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it. To enable multiple ownership, Rust has a type called RCT, which is an abbreviation for reference counting. The RC type keeps track of the number of references to a value, which determines whether or not a value is still in use. If there are 0 references to a value, the value can be cleaned up without any references becoming invalid. Imagine RC as a TV in a family room. When one person enters to watch TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because it's no longer being used. If someone turns off the TV while others are still watching it, there would be an uproar from the remaining TV watchers. We use the RC type when we want to allocate some data on the heap for multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner, and the normal ownership rules enforced at compile time would take effect. Note that RC is only for use in single-threaded scenarios. When we discuss concurrency in Chapter 16, we'll cover how to do reference counting in multi-threaded programs. Using RC to share data. Let's return to our cons list example in listing 15.5. Recall that we defined it using a box. This time, we'll create 2 lists that both share ownership of a third list. Conceptually, this looks similar to figure 15.3. 2 lists, B and C, sharing ownership of a third list, A. We'll create list A that contains 5 and then 10. Then we'll make 2 more lists, B that starts with 3 and C that starts with 4. Both B and C lists will then continue on to the first A list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. Trying to implement this scenario using our definition of list with box wouldn't work, as shown in listing 15.17. Listing 15.17, demonstrating we're not allowed to have 2 lists using a box that try to share ownership of a third list. When we compile this code, we get this error. Use of the moved value A. The cons variants own the data they hold, so when we create the B list, A is moved into B and B owns A. Then when we try to use A again when creating C, we're not allowed to because A has been moved. We could change the definition of cons to hold references instead, but then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. The borrow checker wouldn't let us compile let A equals cons 10 and reference to nil, for example. because the temporary nil value would be dropped before A could take a reference to it. Instead, we'll change our definition of list to use an RC in place of the box, as shown in listing 1518. Each cons variant will now hold a value and an RC pointing to a list. When we create B, instead of taking ownership of A, we'll clone the RC list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in that RC list. We'll also clone A when creating C, increasing the number of references from 2 to 3. Every time we call RC clone, the reference count to the data within the RC list will increase, and the data won't be cleaned up unless there are 0 references to it. Listing 1518, a definition of list that uses RCs. We need to add a use statement to bring RC into scope because it's not in the prelude. In main, we create the list holding 5 and 10 and store it in a new RC list in A. Then when we create B and C, we call the RC clone function and pass a reference to the RC list in A as an argument. We could have called a.clone rather than RC clone reference to A, but Rust's convention is to use RC clone in this case. The implementation of RC clone doesn't make a deep copy of all the data like most types implementations of clone do. The call to RC clone only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones, and we can disregard calls to RC clone. Cloning an RC increases the reference count. Let's change our working example in listing 1518 so we can see the reference count changing as we create and drop references to the RC list in A. In listing 1519, we'll change main so it has an inner scope around list C. Then we can see how the reference count changes when C goes out of scope. Listing 1519, printing the reference count. At each point in the program where the reference count changes, we print the reference count, which we can get by calling the RC strong count function. This function is named strong count rather than count because the RC type also has a weak count. We'll see what weak count is used for in the preventing reference cycles turning a reference counted pointer into a weak pointer section. This code prints the following. We can see that the RC list in A has an initial reference count of 1, then each time we call clone, the count goes up by 1. When C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call RC clone to increase the reference count. The implementation of the drop trait decreases the reference count automatically when an RC value goes out of scope. What we can't see in this example is that when B and then A go out of scope at the end of main, the count is then 0, and the RC list is cleaned up completely at that point. Using reference counters allows a single value to have multiple owners, and the count ensures that the value remains valid as long as any of the owners still exist. With immutable references, a reference counter allows you to share data between multiple parts of your program for reading only. If reference counters allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in Chapter 4. Multiple mutable borrows to the same place can cause data races and inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the RefCell type that you can use in conjunction with a reference counter to work with this immutability restriction. RefCell and the interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrowing. We haven't yet covered unsafe code. We will in Chapter 19. We can use types that use the interior mutability pattern when we can ensure that the borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer type is still immutable. Let's explore this concept by looking at the RefCell type that follows the interior mutability pattern. Enforcing borrowing rules at runtime with RefCell. Unlike a reference counter, the RefCell type represents single ownership over the data it holds. So, what makes RefCell different from a type like a box? Recall the borrowing rules you learned in Chapter 4. At any given time, you can have either, but not both, of one mutable reference or any number of immutable references. And references must always be valid. With references and box T, the borrowing rules invariants are enforced at compile time. With RefCell, these invariants are enforced at runtime. With references, if you break these rules, you'll get a compiler error. With RefCell, if you break these rules, your program will panic and exit. The advantages of checking the borrowing rules at compile time are that errors will be caught sooner in the development process, and there is no impact on runtime performance because all the analysis is completed beforehand. For those reasons, checking the borrowing rules at compile time is the best choice in the majority of cases, which is why this is Rust's default. The advantage of checking the borrowing rules at runtime instead is that certain memory-safe scenarios are then allowed, whereas they are disallowed by the compile time checks. Static analysis, like the Rust compiler, is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book, but is an interesting topic to research. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. In this way, it's conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenienced, but nothing catastrophic can occur. The RefCell type is useful when you are sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. Similar to reference counters, RefCells is only for use in single-threaded scenarios and will give you a compile time error if you try using it in a multi-threaded context. We'll talk about how to get the functionality of RefCell in a multi-threaded program in Chapter 16. Here is a recap of the reasons to choose Box, Rc, or RefCell. Rc enables multiple owners of the same data. Box and RefCell have single owners. Box allows immutable or mutable borrows checked at compile time. Rc allows only immutable borrows checked at compile time, and RefCell allows immutable or mutable borrows checked at runtime. Because RefCell allows mutable borrows checked at runtime, you can mutate the value inside the RefCell even when the RefCell is immutable. Mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is useful and examine how it's possible. Interior mutability, a mutable borrow to an immutable value. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, this code won't compile. If you tried to compile it, you'd get the following error: cannot borrow immutable local variable x as mutable. However, there are situations in which it would be useful for a value to mutate itself in its methods, but appear immutable to other code. Code outside the value's methods would not be able to mutate the value. Using a RefCell is one way to get the ability to have interior mutability. But the RefCell doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate the rules, you will get a panic instead of a compiler error. Let's work through a practical example where we can use RefCell to mutate an immutable value and see why that is useful. A use case for interior mutability: mock objects. A test double is the general programming concept for a type used in place of another type during testing. Mock objects are specific types of test doubles that record what happens during a test so you can assert that the correct actions took place. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purposes as a mock object. Here's the scenario we'll test. We will create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota for the number of API calls they're allowed to make, for example. Our library will only provide the functionality of checking how close to the maximum a value is and what the messages should be at what times. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put a message in the application, send an email, send a text message, or do something else. The library doesn't need to know that detail. All it needs is something that implements a trait we'll provide called messenger. Listing 1520 shows the library code. Listing 1520, a library to keep track of how close a value is to a maximum value and warn when the value is at certain levels. One important part of this code is that the messenger trait has one method called send that takes an immutable reference to self and the text of the message. This is the interface our mock object needs to have. The other important part is that we want to test the behavior of the setValue method on the limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make assertions on. We want to be able to say that if we create a limit tracker with something that implements the messenger trait and a particular value from max, when we pass different numbers for value, the messenger is told to send the appropriate messages. We need a mock object that instead of sending an email or text message when we call send, will only keep track of the messages it's told to send. We can create a new instance of the mock object, create a limit tracker that uses the mock object, call the setValue method on limit tracker, and then check that the mock object has the messages we expect. Listing 1521 shows an attempt to implement a mock object to do just that, but the borrow checker says no. Listing 1521, an attempt to implement a mock messenger that isn't allowed by the borrow checker. This test code defines a mock messenger struct that has a sent message field with a vec of string values to keep track of the messages it's told to send. We also define an associated function, new, to make it convenient to create new mock messenger values that start with an empty list of messages. Then we implement the messenger trait from mock messenger so we can give a mock messenger to a limit tracker. In the definition of the send method, we take the message passed in as a parameter and store it in the mock messenger list of sent messages. In the test, we're testing what happens when the limit tracker is told to set value to something that is more than 75% of the max value. First, we create a new mock messenger, which will start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger and a max value of 100. We call the setValue method on the limit tracker with a value of 80, which is more than 75% of 100. Then we assert that the list of messages that the mock messenger is keeping track of should now have one message in it. However, there's one problem with this test, as shown here. Cannot borrow immutable field self.sent messages as mutable. We can't modify the mock messenger to to keep track of the messages because the send method takes an immutable reference to self. We also can't take the suggestion from the error text to use mutable reference to self instead, because then the signature of send wouldn't match the signature in the messenger trait definition. Feel free to try it and see what error message you get. This is a situation in which interior mutability can help. We'll store the sent messages within a ref cell, and then the send message will be able to modify sent messages to store the messages we've seen. Listing 1522 shows what that looks like. Listing 1522 using a ref cell to mutate an inner value while the outer value is considered immutable. The sent messages field is now of type ref cell of vec of string instead of vec of string. In the new function, we create a new ref cell of vec of string instance around the empty vector. For the implementation of the send method, the first parameter is still an immutable borrow of self, which matches the trait definition. We call borrow mute on the ref cell vec string in self.sent messages to get a mutable reference to the value inside the ref cell of vec of string, which is the vector. Then we can call push on the mutable reference to the vector to keep track of the messages sent during that test. The last change we have to make is in the assertion. To see how many items are in the inner vector, we call borrow on the ref cell of vec of string to get an immutable reference to the vector. Now that you've seen how to use ref cell, let's dig into how it works. Keeping track of borrows at runtime with ref cell. When creating immutable and mutable references, we use ampersand and ampersand mute syntax respectfully. With ref cell, we use the borrow and borrow mute methods, which are part of the safe API that belongs to ref cell. The borrow method returns the smart pointer type reference to t, and borrow mute returns the smart pointer type ref mute to t. Both types implement deref, so we can treat them like regular references. The ref cell keeps track of how many refs and refmute smart pointers are currently active. Every time we call borrow, the ref cell increases its count of how many immutable borrows are active. When a ref value goes out of scope, the count of immutable borrows goes down by 1. Just like the compile time borrowing rules, ref cell lets us have many immutable borrows or one mutable borrow at any point in time. If we try to violate these rules, rather than getting a compiler error, as we would with references, the implementation of ref cell will panic at runtime. Listing 1523 shows a modification of the implementation of send from listing 1522. We are deliberately trying to create two mutable borrows active for the same scope to illustrate that ref cell prevents us from doing this at runtime. Listing 1523, creating two mutable references in the same scope to see ref cell panic. We create a variable one borrow for the refMut smart pointer returned from borrowMut. Then we create another mutable borrow in the same way in the variable toBorrow. This makes two mutable references in the same scope, which is not allowed. When we run the tests for our library, the code in listing 1523 will compile without any errors, but the test will fail. Notice that the code panicked with the message, "Already borrowed, borrowMut error." This is how RefCell handles violations of the borrowing rules at runtime. Catching borrowing errors at runtime rather than compile time means that you would find a mistake in your code later in development, and possibly not until your code was already deployed to production. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than at compile time. But using RefCell makes it possible to write a mock object that can modify itself to keep track of the messages it has seen while you're using it in a context where only immutable values are allowed. You can use RefCell, despite its trade-offs, to get more functionality than regular references provide. Having multiple owners of mutable data by combining reference counters and RefCells. A common way to use a RefCell is in combination with a reference counter. Recall that reference counter lets you have multiple owners of some data, but only gives immutable access to the data. If you have an Rc that holds a RefCell, you can get a value that can have multiple owners and that you can mutate. For example, recall the cons list example in listing 1518, where we used an Rc to allow multiple lists to share ownership of another list. Because Rc holds only immutable values, we can't change any of the values in the list once we've created them. Let's add in a RefCell to gain the ability to change the values in the lists. Listing 1524 shows that by using a RefCell in the cons definition, we can modify the values stored in all the lists. Listing 1524 using a reference counter of RefCell of I32 to create a list that we can mutate. We create a value that is an instance of Rc RefCell I32 and store it in a variable named jank, no, just kidding, named value, so we can access it directly later. Then we create a list in A with a cons variant that holds value. We need to clone value so both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. We wrap the list in an Rc, so when we create lists B and C, they can both refer to A, which is what we did in listing 1518. After we've created the lists in A, B, and C, we add 10 to the value in value. We do this by calling borrowMut on value, which uses the automatic dereferencing feature we discussed in Chapter 5. See the section, Where's the Return Value Operator? To dereference the reference counter to the inner RefCell value. The borrowMut method returns a refmute smart pointer, and we use the dereference operator on it and change the inner value. When we print A, B, and C, we can see that they all have the same modified value of 15 rather than 5. This technique is pretty jank. Neat. By using RefCell T, we have an outwardly immutable list value, but we can use the methods on RefCell T that provide access to its interior mutability so we can modify our data when we need to. The runtime checks of the borrowing rules protect us from data races, and it's sometimes worth trading a bit of speed for this flexibility in our data structures. The standard library has other types that provide interior mutability, such as cell, which is similar except that instead of giving references to the inner value, the value is copied in and out of the cell. There's also mutex, which offers interior mutability that's safe to use across threads. We will discuss its use in Chapter 16. Check out the standard library docs for more details on the differences between these types.